Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we will discuss about the velocity triangle and work done efficiency of Kaplan turbine. In our previous lecture, we have discussed about the working principle of Kaplan turbine. Now we'll see how to draw the velocity triangle and how to calculate work done efficiency of Kaplan turbine. So actually this Kaplan turbine also one of the example in the reaction turbine and also one example in the axial flow turbine. This is example of reaction turbine and axial flow turbine. So here we can draw the velocity triangle similar kind how you have done for the Francis turbine also. So like we can consider a blade is there. Suppose this is the blade is there, and in this there is a impact of jet will be there. So impact of jet in the sense the water strikes in this. Now here two things are there. Either we can consider this is our inlet, at this point the water will be struck here, or else we can consider this is at this side our inlet is there. Any one side we can consider inlet. If you consider this is inlet, then this will be our outlet. If this is inlet, this is our outlet. So by that we can draw any side. So let me consider this side. This is our inlet of jet, and this is V1. Impact of fluid on the blade is V1, and that makes an angle of alpha to the blade. That's why it is called blade angle. Okay, and this is blade is there, and this is impact of jet V1. This makes an angle of alpha. If I resolve the velocity of fluid in the horizontal direction, then here I'll get V11, or which is nothing but also we can write this is V1 cos alpha. Similarly, if I resolve this velocity, because it makes an inclination, so we can resolve in the horizontal vertically also. Vertically if I resolve, then I can get it VF1. So here VF1 is nothing but we can write that is V1 sin alpha. And though jet is like water also moving, and after striking the water the band also started moving, so we need to consider a relative velocity. So relative velocity will be here at this point, and this is our VR2 relative velocity, and there is a velocity of blade which will be mentioned U1 like this, and this angle will be our theta angle. Similarly, this is our inlet velocity diagram, and in outlet condition what will be there? As I told you, this is axial flow, so the fluid will be come out from this blade or from this blade with axially like parallel to the shaft. So at this condition our outlet will be like this. So in this for this condition I will get a radial outlet, radial flow, or we can say radial outlet will be there. So radial outlet in the sense will get VW2, or your beta angle will be 90 degree. So this is our VR2, and this is you can write VF2 actually the flow velocity. And here as I told, this will make an angle of like here theta is there, so here we can write phi. But here for the radial flow we have beta equal to 90 degree. If beta is 90 degree here, now see initially it will be like this. Now beta some angle is there, that is beta some angle of 40, 45, 60 degree angle will be there. Now when beta is 90 degree, that means this total will be disclosed here. Then we can write here V2, VF2 equal to V2 here for this condition when it is given radial flow, and this will be our U2. So here VW2 will be 0, and we can write this is VF2 equal to V2. These are some conditions up there. Like what are the terminology we used here for this condition? At the inlet condition we have terminologies like, just I'll tell you, V1 velocity of jet or absolute velocity. Next U1, U2 and U all are same, that is called velocity of the blade, or sometimes we used to call peripheral velocity, and we used to call also tangential velocity. Next, this is VF1 flow velocity at the inlet condition, or we can say the component of velocity in vertically. Similarly VW2, this is nothing but wheel velocity. VW2 not 1, let's consider for 1 for all these things. VW1 is the wheel velocity at the inlet condition, and also we can say horizontal component of velocity of jet. Similarly, alpha is there, This is runner angle, or you can say that is blade angle, and alpha and theta. Theta is the you can say vane angle here. These are the at inlet condition. Similarly, at the outlet condition also we can write, for the outlet condition similar way we can write, this is V2 and this is VF2, both are same here. Now VW2 is 0 here, and this is outlet also, beta is not there, beta is 90 degree we have taken, and another one will be there, that is phi. So these are the terminologies which are used in this condition. Along with that, we have another one terminology, that is DO. This is diameter of the runner. Diameter of, we can say, outside runner, we can say, or outer runner also you can say. Similarly, another one is there, that is DB, or we can consider DH. This is nothing but diameter of hub, because we know that in this Kaplan turbine we need to consider mechanical hub or boss. So that is the condition. That if I draw a diagram, like this is the shaft is there, and the shaft is connected to the boss. The boss will be like this, and in the boss we have like number of vanes are connected to this one. These are the vanes are there which is connected in the vane. So this diameter is, this is our boss diameter, so that was BDB or DS we can say, and this is our runner diameter, outside to, like from this side to this side, that is our DO, outer diameter we can say. So these are the terminologies are there. As I told you, here also I can write one more terminology, that is VF1 equal to, this is V1 sin alpha, and VW1 is nothing but P1 cos alpha at the inlet condition. This is at the inlet condition. Okay. So these are the terminologies which are used in this Kaplan turbine or velocity triangle also you can see. Now we'll go to the work done. In the work done, like how we have calculated the reaction turbine, similar way we can write the work done here. So work done equal to, here formula we can write like what we got for the Francis turbine also, there you'll see the derivations. We can get like rho AV, and the value will be like VW1 U1 plus minus VW2 U2. This was the equation. On behalf of AB also we can write, this is rho Q, and this will be like VW1 plus minus VE1, and this is VW2 U2. Now this is one condition. Now here we need to see where beta is 90 degrees taken. Now for this condition actually one plus minus will be there. This is one is plus, one other is minus. So negative symbol we got when beta is like more than 90 degree, and positive symbol will get when beta is less than 90 degree. And when beta is equal to 90 degree, we'll get this equation in this way, rho Q bracket start. Here VW2 will be 0. You can see VW2 is 0. So we'll get only VW1 and U1 bracket close. That's it. Okay. This is one term. And the next one, this is work done per second actually. This is work done per second. Similarly, if I write work done per second and per unit weight, then the formula will be like 1 by G, and this is bracket VW1 U1 will be there, because G actually here actually one value will be there. W weight is nothing but mg. W equal to mg. In the place of m, you can write rho AV or rho Q. So rho Q will be cancelled. Only this part will be there. This is, yeah, the next one. Third one is, this is work done. Once you calculate work done, we can calculate the efficiency. So efficiency is nothing but we can consider the hydraulic efficiency first. So any efficiency we know that how to calculate. One is output by input. So here for the hydraulic efficiency, what is the output will be there? That is nothing but runner power. Runner power by water power will be there. And this can be like runner power is nothing but work done. So work done we can write, this is rho Q and this is VW1 U1. Water power is nothing but we can write, this is rho G Q H. Now rho Q can be cancelled, and finally what we'll get here, VW1 U1 divided by, this is GH. Okay, and overall efficiency you can calculate also, like this will be shaft power divided by water power. And similarly mechanical efficiency also we can calculate, that is shaft power by runner power. So anyway, these are the equations for work done and efficiency. Along with that, to design the Kaplan turbine, we need some other terminologies. I'll tell you just one by one. Yeah, first one, the ratio of width. The ratio of width to the diameter, that is can be written N, which is nothing but this can be written du by do or db by do, whatever we want you can give it here. If you want to db or du also you can mention like db, let me mention, but same thing I have given there. Now this is one terminology. The next one, this is nothing but speed ratio. Speed ratio. Few terminology also I have told in the previous lecture for the reaction turbine, in the sense Francis turbine. So similar kind of terminology will be used here. Speed ratio also here we need to consider phi, or sometimes used to give by ku, and this can be written like u1 by root over of 2gh. This is speed ratio, and the value of this speed ratio will be vary from like 0.6 to 0.9 the value. And the next one is flow ratio. These things actually why required to design any kind of Kaplan turbine or reaction turbine will be, for that purpose we require this. This is psi, flow ratio psi, or we used to consider sometimes kf. This is also like vf1, flow velocity, with respect to root over of 2gs. Here tangential velocity, here flow velocity. Remaining things are same, and the value of will be like 0.15 to 0.3. Yeah, the next one is nothing but peripheral velocity or tangential velocity, u1 or u2 or u. Also you can write like pi d naught n by 60. So what is the d naught? We know that is diameter of the outer runner part. We can calculate it. This is okay. Now here discharge of the fluid we can write. We know that the formula is AV. So AV is nothing but here area is nothing but we need to write in this way, pi by 4. This will be our d naught square minus dB square into whatever the V. Here V is considered here actually VF1, flow velocity at the outlet condition. And we need to consider some other terminology like VF1 equal to, we need to consider VF1 equal to VF2. Okay, this is the terminology. And yeah, next, here some angles are there like alpha and theta and phi. So how to calculate that one also, let me tell you. Like we can calculate 10 alpha, suppose somewhere the VW1 is not given, then in that condition alpha is only given, means we can calculate like this will be 10 alpha equal to, we can write this is the perpendicular and the base VW1. Similarly, to calculate the alpha, if these values are identified, this can be also calculated. So again we can write this is 10 theta. This is all in inlet conditions I'm talking. This is similarly VF1 divided by this one can be written like VW1 minus E1. And the next one is the outlet condition 10 phi, you can see. So 10 phi also we can write this is VF2, because outlet condition the base is there, that is U2. So these are the formula which can be used to calculate the velocity, like to calculate the work done, efficiency, and to design the Kaplan turbine. So here I have come I have covered many of the formulas here, and these are called like the trigonometric relations. These are actually trigonometric relations which will help us to identify the answer from this. Like when suppose in the question only one velocity will be given and angle will be given, then in that point suppose VW1, we know already I told you VW1 equal to, here if you see VW1 equal to V1 cos alpha. V1 given, alpha given means we can calculate VW1. Similarly, alpha given, V1 given, VF1 also can be calculated. By calculating this one, we can able to find out if suppose somewhere alpha will be not given, some other angle will be given, theta angle will be given, then from that again we need to see this relation. Okay, so like that we need to see where which kind of application equation will be applicable for that. Then you can use this kind of equations for the particular place, and we can solve the problem. And even we can design the Kaplan turbine also. So I hope you understand this lecture. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Mostly, I think I have covered everything. Yeah, mostly I have covered. These other things are there. Yeah. I hope you understand. If you're having doubt, you can give a comment on the comment box. Thank you all.